Alright, let's take a look at another CSES math problem, graph paths 1. So what's going on here? We have a graph with n nodes and m edges, and we want to count how many paths there are from 1 to n that use exactly k edges. K is up to 1 billion, and n is up to 100, and m is up to n squared. So the cool thing about this is that it can actually be solved by matrix exponentiation. So let's actually take a look at why that is. So let Pij be the number of edges from I to j. Okay. It's not really clear in this problem statement if you can have multiple edges between a node, but actually the solution will work either way, so whatever. Right, so let Pij just be the number of edges, right? The number of edges from I to j, and this handles like self edges and everything perfectly. So if you have like a normal graph where there are no self edges and there's no multiple edges, P is just a 0, 1 matrix, right? It's that sort of normal adjacency matrix. 0 if there's no edge from I to j, and 1 if there is an edge from I to j. Notice this is also the number of paths that use exactly one edge, right? So this is solving the problem for k equals 1. Because if there's only one edge, the number of edges is the number of length 1 of one edge paths. So a one edge path is just the edge. So the really awesome thing is that p squared ij is the number of paths from I to j that use 2 edges. Okay, so this is like the really astonishing fact, I think. So why is that true? Well, so what is p times p of ij? Well, so this is the ith row of t dotted with the jth column of p. It's just the sum over k of pik times pkj. So what you can think of this as is brute forcing. Right? This is just how matrix multiplication works. Okay, but now we're going to give it an interpretation in terms of these graph paths. So you can think of it as brute forcing over the middle. Right? If you're using 2 edges, well, where are you after you took the first edge? That's what we're brute forcing over. Let's say that that's k. And so the number of ways to get there in 2 edges is just the number of ways to get to k in 1 edge times the number of ways to get from I to k in 1 edge times the number of ways to get from k to j in 1 edge. Which, again, if we're assuming like a normal nice graph with just 1 edge, this is just can be at most 1 path through k, and that's only if there's an edge from I to k and an edge from k to j. But notice that this works perfectly if there's like multiple edges from I to k or something. And actually, we can make sort of a much stronger statement, the same logic. Okay, so this works for like any powers of p. So let's sort of show, I guess we're going to do some like induction. P of kj. Okay, so like p to the n is the number ij n edges. Right, and this actually will be enough to solve the problem. Right, so let's say we have p to the a times p to the b of ij. What's that? Well, it's just the sum over k of p to the a ik, t to the b of kj. And so this is the number of length a plus b paths, right? These are length a paths and length b paths. So pi times pj is the number of length a plus b paths from I to j. And why is that? Well, again, we're just brute forcing over the middle vertex. And by the middle this time, I mean the one that you get to after a edges. Right, so the number of ways to get from I to j in a plus b steps, well, you could brute force over where you are after a steps, and then it's the number of ways to get to that middle vertex in a steps times the number of ways to get to the end vertex from there in b steps. And if you sum over all middle vertexes, that's actually all of the ways to get from I to j in a plus b steps. So that's why this is true. So matrix multiplication really beautifully corresponds to like traversing paths in a graph. And so how do we actually solve this problem? Well, we're just going to build up this matrix P based on the input, and then we're going to raise it to the kth power, and then we're just going to read off the answer. So let's do that. Okay, so n, m, k, fine. And we have P, n by n matrix that starts at 0. And then we can read off, read in the n edges. They come 1 index, probably, so we can 0 index them. Yeah, they do. They're from 1 to n. And then if there's, well, okay, if there's an edge from A to B, then just add 1 to Bij, right? That's what we said. Okay, so now we've generated P, but we actually want the number of paths that use k edges, so let's generate P to the k. And then the answer will just be P to the k from 0 to n minus 1, right? Because we want the paths from 1 to n. And so, you know, again, we need a 0 index instead of 1 direction. And that's actually it, right? This pk counts the number of paths that use exactly k edges between any two vertices. So we just want, you know, 1 and n because of this argument. I think that's really sort of amazing. Okay, so now we just need to implement matrix multiplication. That equals grid vectors, right? Because we want the number of paths modulo 10 to the 9 plus 7. Of course, we do. Everything is modulo 10 to the 9 plus 7. Okay, and because we are taking dot products to matrix multiplication, we need to add and multiply. Okay, to get map pow, we need, you know, we're going to build power out of multiplication, so we need to build the multiplication. And this is totally arbitrary matrix multiplication, by the way. We're not like using the fact that all the matrices that we're going to be multiplying are powers of some matrix. I don't think that really helps much. It's not like any easier to handle that case than to just handle the general case. So I just always type general case that we're practicing. So that's matrix multiplication, right? Just Cij is the dot product of the ith row of A and the the jth column of B. So now that we have matrix multiplication, we can do matrix power using exponentiation by squaring. Right, it's an amazing trick that lets us get exponentiation in logarithm of time. Right, and you know, again, the magic trick is that a to some even power is just a squared to the power over 2. So that should be it. Okay. No. This is supposed to be map mul. Suppose we should declare A and B before we read something into them. This is a mat. Cool. Okay. Try it on the sample. 2. Well, that's definitely something. Ooh, too slow, really? Okay, because our multiverse multiplication is n cubed, and I guess n is 100, so that's like 1,000,000 operations. And how many multiplications are we doing? We're doing like logarithmically, you know, log of 10 to the 9, which is like 30. So I think the problem here is that we're doing too much modding. Is this so clear though? Because each of these values are only up to 10 to the 9, but when you multiply these, they're already quite large potentially. So you got to be a little bit worried about overflow. I do wish that the time limits on CSES were like a little bit less tight, so I would not have to deal with this this problem. Okay, I think I'm not going to deal with this right now, and I'll explain in the description of the video how to solve it. Because the thing that I actually want you to take away from this is this idea, right? That starting with the adjacency matrix of the graph, you can raise it to some arbitrary power, and then you get the number of paths of that length. Because matrix exponentiation corresponds to brute forcing over, or sorry, matrix multiplication corresponds to brute forcing over the middle vertex in the path. So yeah, that's the problem.